So hopefully when the world's on this side of the clock, jump into a lot of words that probably don't mean a whole lot right now. But I'm James. I work at Interact Labs, which is a small kind of bespoke vulnerability research joint. Covers pretty much all the topics, mobile phones, the embedded systems and stuff like that. That's pretty much my background. I'll do a lot of embedded system stuff. I touch basebunch on a pretty regular basis. So quick kind of rundown what we're going to cover today. A bit of a primer for all the background knowledge. So how semiconductors are put together, how we can unput them together, so deprocessing them, what electron microscopy is, how we can use that for reverse engineering. We'll touch a bit on focus ion beams and kind of a hobbyist scene uses. So let's jump into it. Why would we want to reverse engineer silicon in the first place? It seems a bit excessive, right? Kind of one of the big ones is photos on the attack surfaces that would traditionally be looked at from a vulnerability research perspective are getting smaller. The smaller they are, the easier it is to make it more secure on the vendor side. So it's becoming increasingly more difficult on that front. There's a lot of solutions, commercially off the shelf for security. So you get things like TrustZone, JSE, TPS, many more. That does make life difficult as an offensive security researcher. Kind of the other big frustration these days is parameters encrypted using keys that are implanted in silicon. There's not a whole lot you can do with that unless you're actually copying to reverse the silicon in the first place. So it's another one of those chicken and eggs. Again, if your attack surface has zero byte left in it, what do you do with it? That's also a nice big skill issue. And kind of another big one is traditionally where we would like to extract firmware from a hardened target, we would go into fault injection and side channel analysis type attacks in the past. Vendors have kind of significantly invested in this case in the past 10 years, so that's become an increasingly a thing of the past for the most hardened targets as well. The other good thing about silicon RE is for a single revision of the die, it's kind of a fixed cost investment. So you do it once and roughly hence all revisions of the die that it's in. That fixed cost is quite high initially, but it is fixed. Silicon is the ground truth. It has to be there. You can only really obscure and make life more difficult, but it will always be implemented on that die somewhere. And kind of the most important reason is pretty clear. So that's kind of all the efficacy into. So silicons and semiconductors. We've got to do a bit of background info before we can jump straight ahead into the SEM stuff. So semiconductor circuit design, kind of the modern processes are no human in the loop. So you would have an input HDL language like HDL or Verilog. That goes through this whole convoluted sequence synthesis, through like writing the pop tree, bar tree, like all that sort of synthesis. For us, from a reverse engineering perspective, the most important ones are how circuits are actually routed onto the die and general floor planning. So, the final output form is a format called PDSI2. Kind of initial format, and it's been around for the longest time. It defines these polygons that you see at the bottom, and that's how individual transistors stack up before you do your orthography stage. That's kind of where the traditional tape-out terminology comes from, because it used to be transferred around the magnetic tapes back in the day. So this synthesization process, what's that look like in a bit more depth? We have an input HDL language, HDL, Verilog, anything of the sort, similar. The next step is mapping that to the PDK, so process development kit. This is what like a semiconductor or silicon foundry will give you as a customer of theirs. Effectively, in this case, you probably can't see that, but that maps across the single cell, which is just an input buffer. And the PDK basically defines the sequence of polygons, and that's how that is implemented in reality in tape-out the chip. So, this buffer is a single standard cell. Standard cell is effectively a a cell that shoots across many thresholds. It's the basic building blocks of your semiconductor. The final chip is made up of many standard cells. So to give you an idea, that's a very minimal chip on the right side, and that single standard cell there is on the left. So just to get an idea of the scale, in reality, like your Intel chips or on any of the other vendors, it's on millions of volts, magnitude bigger than this. So yeah. So your GDS2 sort of output on the synthesis process is taken in other foundries. They do the whole standard semiconductor process sequence, put it on top of the sort of attaching the die, wire bonding, and then the final packaging, which is kind of interesting for us as reverse engineers. Again, the die itself, silicon based, it has to be attached to something that you can actually electronically couple with. So this is typically like a lead frame model, I should say, which has pins come out of it, and that's what you'll see in the edge of your chip. That's what's soldered on the PCB. So yeah, kind of a couple of different styles. It's the traditional lead chip, it's kind of flip chips and stuff like that. You'll see kind of older styles there, rather than flip chips. It's more PGA mounted stuff, and the lots. Yeah, and kind of unfortunate for us as reverse engineers, these processes are kind of one way. It's quite difficult to undo them without some pretty nasty methods. So looking at these bonding and packaging techniques in a bit more depth, this is kind of what it looks like. So again, the traditional style is you have your silicon die in the middle, and then you've got wire bonds that come off that and create actual pins. So a pole bond is the other style, and the wave bond is lower than the bottom. And that's how the silicon die is connected to the outside of the paper. The machine that does this is just a wave bonder, or typically these days in a standard semiconductor setup, you have an automated line. It does all the bonding automatically. These are more fun to use. So looking at what the entire semiconductor looks like in the cross section, this is kind of the makeup of it. So you have a bunch of interconnect layers, which is effectively, if you know how PCBs work, you have all the traces. It's basically the same idea for a die. And you have a bunch of metal layers, it's smaller and smaller and smaller as you go down. You have these two silicon bodies that connect every metal layer vertically. So vertical connection is done to the two silicon bodies, and the metal straps basically horizontal metal. So, and yeah, to give you an idea, sort of could be anywhere from like six layer die all the way to like metal 50 and stuff these days, so very small process size. So yeah, that's how semiconductor dies are put together. We don't really care about that so much. We care about getting the die back out. So how do we process them? We'll do this one briefly because there's a bunch of laws in the UK which kind of suck if you want to do this stuff. So we'll just skip over this. But a bunch of methods for actually decapsulating dies by the epoxy setting. A lot of these are chemical based. You can use more mechanical methods. Milling it out very precise CNC. That gets you down to like a specific level, but then still do kind of the wet etching to go on the useful. And then again, some of the less useful techniques is sort of thermal pyrolysis to heat up the epoxy to a point where you can crack and extract the die. And flip chips are actually ironically kind of the easiest. You can just heat it up and the heat shield kind of falls off and the flip chip process. So those are quite nice here. Encapsulation exposes the die from the epoxy setting, but because the die has a bunch of metal layers, typically we're interested in the transistors at the bottom, the actual logic, which means we have to remove all of these metal layers on top of that. And this is a separate process called delayering. Again, pretty nasty chemicals involved here, like hydrochloric acid. That's not the best. You can also do some more advanced stuff if you have access to use or a lot of money. So there's rectifying etching. Chemical lapping is kind of the older technique. You can get really good at it by hands. So this is the nice entry-level way. You basically have a lapping machine. You mount it to a in a rotary fashion, you just wrap. The issue with mechanical wrapping is kind of the narrowing. The die can get a bit warped, at which point you sort of unequally etching through layers that you care about. These sort of more advanced techniques that come about in past 5 years brought on anyway. It's a very high removal rate and it's also quite accurate. And again, using it for the time we get onto later. So the main topic of the talk itself, scanning electron microscopy. What actually is it? And what is it there? So, yeah. Kind of one thing that's covered is why you need to use the scanning electron microscope in the first place, and that is because traditional microscopes that we use for IC reverse engineering in like the 90s and 80s, they're limited by this thing called obvious diffraction limit. So the wavelength of light effectively limits the theoretical maximum resolution of this microscope, which kind of prevents us from looking at the most modern node sizes and guys. But for electron microscopes, you're using electrons instead of light. So the wavelength is much smaller and you get a much higher ultimate resolution. But yeah, that's pretty boring. For a lot of maths, no one really cares about that. So what does it look like in reality? This is kind of an example of how this map talks real life. So we have a particular TSMC process here that may or may not be involved in SEM, and that's under a normal optical microscope. A region of interest that we care about is on the left side of the die, and this is kind of the ultimate resolution that we can obtain with the optical microscope. So you can kind of see stuff, but it's a bit of a blur and not too easy for us. We jump up to the electron microscope. This is kind of the same region under the electron microscope. The ultimate resolution is very much higher. I can actually see the individual structures there. So yeah, you can basically see the hologram. These are TSMC structures, which we'll talk a bit about later. But yeah, for us as reverse engineers, this is kind of the thing that we need to use on modern dies. There's yet again a sort of further tool, which is used for reverse engineering. We'll talk about it anyway. For the transmissional electron microscopes. Yeah, if you need to use one of these, you know why you need to use one of these. But the reality is it's hard to apply the ultimate resolution and the sample calculation to these plugin and that is to semiconductor dies unless you're doing actual process analysis of the material you're using inside. So, scanning electron microscopes, critical systems. Let's have a look at these systems as a whole. You have the sort of older traditional style and the new stuff that you'll find in your local university or research facility. For all intents and purposes, it's much the same. You have an electron chamber on the left, the electron gun assembly, which is the top bit, and some sort of monitor to actually this. Otherwise, there's a bunch of detectors, which is kind of these pointy rectangle things pointing to the chamber. And that's kind of what does the imaging for us. So these are quite important. For electron microscopes, it's not quite as simple as just putting your semiconductor dot under it, like an optical microscope. There's a bit of an involved loading sequence for the vacuum chamber. So in the old days, that would be about nitrogen turning the chamber, loading the sample in on the sample holder, putting the whole thing back on, and you have to pump back down the high vacuum. It's a bit of a process spinning on about fingerprints of hydrocarbons basically on not friendly cells. So you do what works through the whole process in tools that are traditionally putting in top stuff. Yeah, otherwise you'll end up with like prolific aberrations or lower ultimate resolution of the SEM. It's being made slightly better these days with sample exchange slides like this. You don't have to purchase the entire chamber as opposed to a small global exchange chamber. So that makes the process a lot quicker than the traditional 15-20 minute sample exchange routine. So yeah, kind of from top down, the SEM itself has this electron column assembly. You basically have your ego at the top, which is electrons, just a couple of ways it does that, and then a bunch of lenses that do condensing. And kind of the important as well is the raster coils on the bottom. So what these are doing is, if you know how CO2 is the CVs, that raster sequence is basically the same, but instead of picture being produced with an electron beam. So, same technology, pretty much. The other one that's kind of important for us is reverse engineering is the different sources that can emit electrons. The oldest of these is thermal source, which would be like a tungsten, hurricane type thing. These are fine. If you want to do more advanced node sizes, more recent stuff, you kind of struggle with one of these. You really want to switch up to what's known as a field emission filament. So you can see here the difference in those. Tungsten filament field cell is also a much better resolution and has a better intensity as well. So if you want to do something that they were try and get your hands on a field emission SEM or using universities and so, this is kind of the other big one. For reverse engineering, we kind of use this in a couple of ways. So, the way that the electron beam actually interacts with the sample is quite important. It emits a bunch of things when the electron hits the sample. Secondary electrons are quite surface level, so the top of the actual sample is what we're imaging with those. Highly topographic. It's really high resolution as well. What we can do as well is use these backscattered electrons, which are quite important, because they come from quite low down in the sample, which means versus reverse engineering's deep processing the dye is quite hard. So if you can leave kind of a thick cluster on the top and use backscattered electrons that can move below, you give yourself a bit of wiggle room there in terms of not destroying the conditions of the point, but also being able to image quite far down the sample, quite thin microns. Again, as it says, it's quite useful for cheating and revealing. So the other interesting thing about backscatter electrons is their intensity is kind of directly proportional to the atom that they're interacting with, the Z number. So different elements will appear at different intensities, which is quite a useful thing for semiconductors, because obviously you have different materials in there, like copper and tungsten, the aluminium and traps as well. So you can kind of use that to figure out what materials are used. Instead of things like the reverse engineering. The kind of interesting one again, as said with the PhD stuff, electron energy dispersion spectroscopy, quite a mouthful. That abuses the Z number stuff so that we can literally identify materials in this format. So that was a lot of words. What does this actually look like with detectors in situ? This is what your typical secondary electron image looks like. So quite high resolution, and you can see the top layer of the surface. You can kind of see some stuff down below, but again, that offset layer is pretty thick to actually image the layer below. With all our backscatter electrons, quite a stark difference. So you'll see that it's a lot more elemental focus. We can see these tungsten fibers are quite bright because it's a number of tungstens really high. So that's quite useful for identifying different aspects of our semiconductor die, and then also useful when we come to reverse engineering and circuitry board. The other nice one is the EDS. So we can actually tell that these tungsten elements consist of this chemical composition. Elemental composition, so you find colors with elements, and we get the entire element in composition, which is a good part of the image squares. So that's kind of how the SEM actually produces an image. What we need to do is scale samples in there. Sample preparation for SEMs is a bit more involved. So for most SEMs, they need to be completely dry, which is a bit more, especially if you're using chemicals at some point to do there. So we have to put them through some kind of critical point dryer, heat them up with silicon furnace. Specific SEMs can handle these kind of highly wet things, but really like for the traditional gold standard SEM, which is one that you can buy, you really want to try dry samples that aren't highly pretty solid. Again, kind of about hydrocarbons, not friend of an SEM, these can be pretty clean, so you can go through the traditional sort of cleaning cycle, micro-90 ethanol, and is pretty much the standard. the thing about SEMs is that it needs to be conductive or have at least a solid path to grind. So you may need to cope with something. For some semiconductors, you get away with it. For others, not so much. This is sort of a different process called thin film deposition. You use something like sputter cutters, but it's very thin film of gold over your sample. It's not good for using this as well. And there's just kind of microsamples on, so it's just a little, and you use like a piece of copper foil and the stick or something that we pile under that, and we could scale an image. So, sounds a bit fickle at times. There's quite a few imaging artifacts that can run into, such as stigmatization, like this. You have to correct this pretty often, especially when you're changing zoom levels, which can get credit for shooting, but it's quite easy to see, especially if you have a circular object. You should see the signals shift in both directions as you change the signifier coils on the signal. And the other big one is sample charging. So again, if you're seeing this with your semiconductor die, that means it's not a good enough ground return path, or it's simply not good enough. So this kind of charging on the left, the image should sort of you pull that, sort of jumps in and out, jaggedy, you want to get a sample of the imaging parameters that you have control of. For us, it's not finished. We need to really be concerned with here is primarily the beam current, and then you kind of protect it with the using quite a high beam current, quite a high accelerating voltage. It's not good for the lifespan emission, but it's pretty much the ideal semiconductor imaging setup. So that's what we do. Yes, we just need to choose those and then switch between secondary electrode detector and tungsten. There's a bunch more you can do with reverse engineering with the key ones. So, what kind of possibilities does this open up for reverse engineering? Once you've configured everything, where would you sample? One of the big ones is mapping out of the sample cells. So, for us coming into reverse engineers, it's very unlikely that we'll know what foundry, what process size, and all these different factors that the semiconductor chip is using in the first place. So we have to go through and map out these sample cells. If you've ever used SLIDA or anything like that, it's quite similar to setting up a type library of structures that are on them, but in this case it's semiconductor structures. So different sample cells, you may not actually know their function, but if you find them and then find their instances, you can start reversing the chips in. These are kind of the discrete building blocks. So if you understand these, we can reverse engineer the chip in its entirety. And a lot of times we'll have custom standard cells which implement fiber IP blocks and silicon path security. So these are quite important going on. There is sort of limited options for doing a full netlist reconstruction. So this is effectively, if you know the standard cells and you can image each layer effectively, you can reconstruct the entire chip back to netlist, and in some cases back to a history layer. So instead of reverse engineering small segments of the chip, effectively have an entire clone of it. These are like six-figure investment type tools, so very few people are using. However, they do exist and it is an option. So outside of mapping out the standard cells, for us as reverse engineers, something that's quite important is fuse structures. So with an example here, semiconductor fuse is effectively a structure that looks like this, and it enables you to one-time program something as effectively 0 or 1. And typically you'll see used or abused, I guess, in semiconductors to store configurations such as super J-type port being enabled, or also things like crypto keys that are used for derivation down the line. So if you can image these in a sensible manner, you get keys of things effectively, which is so nice. These can vary from country to country, but TSMC is a pretty good one to focus on, given how big they are. The one on the right is a standard TSMC fuse region, and these particular ones are globally or programmed, I guess, at boundary by passing an excess of current through, and that's supposedly the existing time. There's a couple of other methods for like bigger fuse sizes. This one's like 3 micron across. You can like laser trim, use like fibers that cut the line in the middle. However, unless you're looking at older stuff, these are less likely to be encountered. So if you want to take an array of these uses and decode that as something sensible, then I have to follow this process, which is in high definition, so probably a secondary electron detector image by region. And let's stitch all of these individual image files together. And then we need to do fuse identification. So in a lot of cases, it's just like an OpenCV script that does pattern matching on this structure, and then like an open line in the middle is a very simple one of this. The other one is how these are accessed. So if you have an array of fuses, how each column and each row actually accessed, are they linear, so left, right, up, down, or is it a scrambled manner? So you need to go back, reverse engineer more circuitry. And then the kind of nice thing that we can do is if you understand how these are addressed, we can just write our own HTML script with the extracted bits and we get back the actual values. These will contain some pretty spicy things, so you'll see it not only looking for no images there. So outside of fuses, quite another interesting thing is mass drums. So this is basically this silicon wedge, so some firmware, some bootloader, but it's all usually pretty low level, so it'll be the initial bootloader that does all this turbo burnout or something like that, which is quite a nice target for us in the vulnerability researchers or reverse engineers. It's quite a similar process to how we look at fuse banks. So again, you have the individual bits that are encoded. There's a couple of ways that they do that. However, again, we just need to go through and understand the whole number of coding, and we can do an image with it. You can see an example there of what that looks like in reality. You get the individual bits out, then better point we can do it. So that can oftentimes be a pretty easy process, depending on the vendor. Otherwise, it would be a bit of a nightmare going back and reverse engineering, following the code. So pretty variable. That's kind of the 3 main things that we can do with a scanning out from Microscopy, which is quite useful as a reverse engineer from the research. Kind of the next big thing is outside of SEMs, you have focused ion beams, which are very similar machines, except instead of using electrons, they use ions to bombard the sample. So, not too dissimilar. You're using ions. Traditionally, they used to be their own units, but now we've got cross-beam units that have a SEM and a FID built in, so you can image and use the FID as different types of FIDs. So, you've got Kelvin FIDs and xenon P-FIDs, which, as a reverse engineer, we're not really using those for anything fancy, although the fact that they can remove material much quicker. The primary use of the FID is use the ions to ablate stuff from the surface of the target. So you can actually use that to expose particular parts of the chip. So one metal layer down or 2 metal layers down. But also use a precursor gas. This effectively means you can deposit material. So if you want to deposit like platinum or gold or something else on the surface of the chip, you use a precursor gas to do that. So quite versatile machine for reverse engineering. So the precursor gases go through the system called the gas injection system. It's effectively just a bunch of nozzles that are quite small and direct gas where you need sampling surface. So you can use this to accelerate the etching rate, which is quite useful for delayering the chip layer by layer. But again, you can also use it for deposition. So you can see an example here of the lines where a precursor gas can use to deposit a platinum line across. In our case, as reverse engineers, the primary use case for this is doing something called a FID circuit out, which means you can literally edit the functionality on the chip in situ, but we'll talk a bit about that. There's a bunch of different materials, either platinum's the most useful one, and potentially tungsten as well, of course. There are some artifacts that can be introduced by FIDs, but shouldn't really matter for most chips that you're working on unless it's like 3 nanometers or something, because you should. they're quite expensive again, but pretty much everything with fibs and is a money pit, so don't discuss. And yeah, so the big one as well is silicon fluoride, particular gas test, which increases the edge width exponentially, particularly for silicon, which is quite useful for us as a semiconductor relationship. Yeah, I mean, it's selectively etched silicon like this group here, which is quite a bit higher than normal. Kind of what you're trying to optimize here is how much time you need to rent on a fib versus what it's seen on the fluoride is, and this usually wins out the better options. Yeah, so I mentioned fib circuit at its briefly before, but explain what that looks like in reality. Obviously, you have all of the metal tracks, so copper, aluminium, and the chip. And that's how functionality is implemented at its lowest level. But with the fib, we can just change it arbitrarily. So if they have a latch condition that says J-pipe should be disabled, we can just place a line that says no, J-pipe should be enabled. This isn't that way. That does kind of cut out a lot of the work to get there in the first place. Probably about 14 hours worth of visualing. Once you're at that level, you can just edit arbitrarily. So it's pretty much the ultimate cheat code for semiconductor. And that seems like quite a bad thing if you're semiconductor vendor. Like, what can you do to prevent this from happening? And so, ordinary countermeasures. There's a couple of things that they've tried. So, for like our ROMs and our fuse banks, we have the Kalman decoders. At a very basic level, it will usually be linear, so left, right, up, down. For all of our bit lines and our load lines, but some semiconductor vendors somewhere thought, what if you scramble these so it changes the order in which that happens? It's kind of like, okay, that's the thing you can do, but it's like another 15 minutes of work to figure out what's happening. So again, basically a waste of time, but they do it. I guess it prevents some very low effort attacks, but you can even dump like the entire storage cell array and just run every permutation until you get back a likely candidate that looks reasonable. So there was an effort, but really poor one. Something else that they tried is sort of active shield meshes. This is on the very top layer of the chip. You have a bunch of these metal lines, they run around. You typically see this in secret elements, so TPMs and stuff like that. They like to use these active shields quite a bit. And basically the way it works is you punch the lines, they get right back onto the chip. If one of those is severed, it's monitored, and the chip is either wipes from contents or it just ceases. So that's pretty annoying. And kind of their goal there is to prevent something called microcurving, where you have a needle, you can touch the chip, so it's basically like very small bulk needle. But again, basically this time, because of the fib, you can just trace out all of these lines, figure out where they go back to. So you trace them all, figure out where they go in, and then it's a single fib circuit that away from being basically just so you can disable the entire shield and continue on with the would normally. So yeah, I mean, again, another vendor effort about a mitigation, but pretty cool one. One of the best ones, ironically, it uses one of the aspects of semiconductor deep processing, which is called an edge effect. So typically when you're delaying a chip via mechanical means, you're lapping it around in a rotary fashion and a little cut with adhesives to try and remove material gradually. However, the abrasives gather at the edges of the die, so each of the leading edges will have a little bit more abrasive on it. And this leads to the edges of the die going unevenly. So that's quite bad because you lose a lot of information around it. Some genius, one of the vendors, figured this out. So they started to place all of their sensitive structures, such as crypto keys and anything that does secure different right on the edge of the die. So again, this is the TSMC example, where the viewpoint region is literally directly on the edge of the die, which is quite annoying. Close to that, you lose all the crypto, which is kind of the end goal for a lot of these products. So, again, this one's actually pretty good countermeasure. It does make life pretty difficult and reduce your success rate. However, 20 million back in like 2008 came up with an idea to use like a sacrificial pad. So slice a bit of another silicon die off, it's the same height, place it on the leading edge, and you basically protect that region. So you put a silicon die, fuse regions, and it reduces the amount of basically that. So you have a pretty good success rate from using a lot of information. So I think 3-for-3 mitigations are all pretty useless. It does kind of increase the amount of techniques you can use, but at the end of the day, it's still doable. There's a couple of other things like SRAM puffs that are used so that due to the increased costs and that kind of thing. So those are the three big ones. They're all pretty useless. So all of these SEMs sound pretty expensive, right? Like baseline one would be £160,000. That's pouring precursor gases. How do you do this as a hobbyist? Is it even feasible? You'd be surprised. eBay's your friend. eBay Plan Designer and your local ones. Keep tabs on it. There's a lot of surplus university and laboratory credits. I think TPK has one of them with SEM, so it'll range anywhere from like 2 to 3K up to at the end of the difficulties. So always want to keep an eye on some alerts. Some labs go through periodic refreshes, so SEMs are actually pretty good. So some of the older tungsten ones can be quite cheap. Again, because of the size of these things, they're like 300 kilograms as well. They won't rate them quite quick, so you can oftentimes lowball all of these settings down to like ridiculously low values. Third-party recyclers are pretty clueless about how the SEM actually works. That's another pretty good bartering tactic. You can say, oh, it's missing X, Y, and Z, and it's really not. They tend to estimate near the original resale value. They'll ask for like £135,000, but in reality, this is a SEM that's being decommissioned improperly. So it's going to require like 3 weeks of work to get it back into the semi-function state. So you can use that to your advantage. The reality is that these guys who own these, they have just come into a big lot of electrical stuff that they're not going to buy. So again, barter down, that's the key. So the other big advantage for us is no legitimate business is purchasing a second-hand SEM. You're buying like the model that you can afford from the vendor. So many risks associated with the second-hand SEM from what's been loaded in there before. Is it like something horribly radioactive or some horrible chemical? Does it even work? What work needs to be put in to maintain it? Will the provider still provide a service contract? So I don't really know what these guys still are who's trying to sell these. It just be practical. The other good thing to do is there's a bunch of stuff out there. So like hundreds and hundreds of websites that are basically seeing the list there. It's above views. Monitor all of these. Don't get IP banned. That is a lesson. But yeah, the stuff that we have pretty cheap. We've got 3 cases on Google Analytics again, pretty cheap. So the other big one is do not contact SEM vendors because you'll have sealed issue for like the next 3 weeks. So that's always fun. Always trying to arrange meetings. I don't know about you guys, but I don't have 160 points in SEM. So bit of waste of time for everyone involved. The best way is meeting up with people at conferences. So it's quite a big one once every 2 years for MMC. There's a lot of vendors there, but also a lot of service people who are pretty forthcoming with schematics and service manuals. So meet the right people at those kind of conferences. You'll get a bunch of Japanese documents that can be translated across. That's the key. Avoid the sales people, meet the right people at conferences, and you're all sorted. That sounds good. However, there are some partialities associated with electron microscope ownership. It's a pretty awful idea, all in all. Some pretty difficult professions involved. Also high vacuum systems. You don't know how these work, potentially how to repair these, the machining, how the flanges work. Electron optics, which is like the entire field of itself. They don't like being dropped. A lot of the second-hand ones have been dropped on the side, so that's not a good aspect. The maintenance is pretty brutal. Like a turbine electric pump alone could set you back up £1,300, so not fun. And putting them all together in one thing is basically like the worst case scenario as a hobbyist. Not a good thing to do. Better to know a friend, I think, I suppose. yeah, it's pretty feasible to do some of this stuff even wide. And the detectors have an important aspect. These are and that's what you use it image. So if you break one of these, you transfer if you want different imaging types, such as high-tech electrons. There are some case studies, bunch of friends and people in the industry who do have these. Vladimir, that's just his garage. There's like 3 SEMs in there, a bunch of motorbikes. As you do, it can be done, but it's a lifelong sort of activity of collecting these things. Peter, over in the Netherlands, got a bunch of SEMs, but also Dance Dance Revolution machine. With SEM. These things don't like vibrations, so that's not an ideal setup for your SEM. However, pretty good nonetheless. Spirit in Belarus, got a bunch of SEM in his apartment. I believe he's like close to exceeding the floor's weight load rating there. That's like 400, 500 kilograms on the edge of what's actually suitable for that apartment. There's a couple of others. A lot of these people want to remain anonymous because the SEMs have been sourced from universities that tend to be things have been disposed of, but maybe they haven't been. So a lot of that, a lot of people that know someone that has access, so quite close and daggers really. And me, I got into this sort of rabbit hole 1 or 2 years ago now. It's a massive amount of work, it's good fun. So I got a bunch of stuff in the apartment. I think I'm up to 2 SEMs now. These are little desktop ones, so they're a lot more usable. However, they did require a lot of repairs, so not great unless you can't spec them out like a £160,000 machine. And that's kind of the same headache that isn't with it. Conclusions. Pretty awesome things. If you get your hands on one, it does open up a new world, reverse engineering and vulnerability research. They're not cheap, but do try and get involved. Good way to get your toes tipped in is your local university. You can rent it all out, take some samples in, they'll teach you how to use it. Maybe don't bring sensitive IP or external fuse banks in. They may not appreciate that. However, in most cases, they're willing to help. So do try and get involved. They're fun with machines. If you have any questions or interest in this kind of thing on our own business, send a message or something. So that's pretty much everything. Thank you for listening.
You mentioned detectors kind of passing at various points.
Yes.
I work with part of my detectors. You're getting close to 6 figures as well for
new ones.
Is there a similar sort of market for the second-hand one where you can that's just your camera? That is.
Yeah, so you can kind of get away with that at like the open days where they have like a lab there on. You can do a bit of that. However, once the sort of third parties get their hands on it, it's very much the best way is you keep buying another SEM that's custom with the detectors and things. So
it's cannibalizing.
Yeah, it's cannibalizing sort of a horrible mess with SEMs.
So you can see so to do that, you have to necessarily get away from the layers. So how would you then
So with the positive fit, you can make very small circuits. So you effectively have a tunnel down, make your own wire to the circuit that you're interested in, the bottom wire. This can get a bit tricky with like the smaller interconnect sizes, however it's feasible. Kind of the other thing that I didn't really mention, which is quite pertinent here, is secure processes. So like stuff like TPMs and Scarlons, they're not going to be 3 nanometer chips. Like these are much bigger, 130 and like 60 nanometer stuff. So it's like actually quite a lot more feasible to fit that it's on than you'd expect. They're quite big processes.
So that also.
Yeah, exactly.
You said you're almost 83 litigations.
Yeah.
Do you have any ideas of how they could go harder?
Not really. And if I did, I wouldn't really give them up. However, SRAM puffs are quite a good one, but they do increase the manufacturing costs tenfold. So you'll see them in very good applications. Yeah. So, yeah. So I mean, that's kind of a one-trick pony, right? Like you'll run into that, but then it's only another key bit out of the way from actually having. So I think that their goal is to increase the cost of the attack, right, to a point where it's only feasible by hand. Like if you do X amount of chips, X amount of time, only a handful of people in the world are going to be willing to invest in it. Yeah.
Yeah, so you mentioned something about firmware so I'm using that. Update firmware getting the from OEM, but then you can't bring that firmware.
Yeah.
Using this, actually, you kind of refits from the chip without, if you're far on the left, is that not how you connect?
You do have specimen beam interaction, but at the lower accelerating voltages and beam currents, you don't cause enough damage to actually blow the bits. With things like the FID, you'll see quite a lot of damage, which is like doing etching, but just as the end imaging, especially at the lower accelerating voltages, you won't cause any damage here. But any noticeable damage.
Extracting mask.
Yeah.
What are we talking in size of ROM? Like petabytes, kilobytes, megabytes?
Yeah, I mean, usually like somewhere 4K up to 16K. It very much depends on the chip and application, but the size doesn't really affect much. Like it's the same process for the address decoding. I don't know how much scrambled it, but it's still the same process. Once you figure out how that address decoding happens, how big the storage accelerator doesn't really matter for all intents and purposes. That's it. Thanks for listening, guys.